Alrighty, so far we've talked about our correlation coefficients. We've talked about the relationships and describing the relationships and scatter plots between two different variables. We talked about correlation and causation, and we've talked a lot about interpreting those scatter plots as well. So now we're going to take a look at actually using a linear regression model to predict some type of values. And we're also going to actually write equations that fit our scatter plot. And we're going to find our line of best fit or our least squares regression line. And we're going to look at interpreting the slope and the y-intercept of the problems as well. So sometimes correlation alone doesn't really provide sufficient enough information to answer some type of statistical or research question that we'll be looking at. Regression can really be used to predict or explain. So our linear regression is what we're going to be looking at next. Is going to help predict, or we can explain some type of variation in one variable to another. Now, maybe you've done this in the past, so maybe you've heard it before where we have our line of best fit. Our line of best fit is really what we call our least squares regression or a linear regression model, or the line of best fit. Really, that's what we talked about in algebra. We're talking about what line best fits the data when we're looking at our scatter plot. So just know that least squares regression or linear regression or line of best fit is going to be essentially the same exact thing that you talked about in algebra. We're trying to see if we have a line that fits the data where all the points are equally above and below our line, and we're actually going to use technology to do that. And then also some other things with our graphing calculators. So when I talk about least squares regression, or in short, LSRL, it means the same thing as line of best fit. Now, we talked about back in algebra where we have our slope-intercept form of an equation where we have y equals mx plus b, where m is our slope and b is our y-intercept. This equation is going to look very familiar to your slope-intercept form, where we have y hat, because this is our predicted line, this is a prediction, and we're looking at ax plus b. So our graphing calculators use a and b versus m and b. So that's really the only difference. The y value is just the predicted y value that we have. That's what our y hat means. I like it gives a little hat on them. The explanatory variable, remember, is always your x. Our slope is going to be our a. And then we have our y-intercept, which is b. Now, there is another way in the calculator, another form in the calculator that you can use. It is y hat, where we're just switching around these values, where I have, that's supposed to be equals. We have equals a plus bx instead. Here in this case, just know that your slope should always be in front of your x. So it's always the coefficient in front of the x. Now, algebra terms, coefficient, number in front of the x. Think of it goes with the x. So really our a is our slope here, a is our y-intercept here, and b is going to be our slope in this special equation. And you can use either in the calculator. So remember, when we're looking at slope of the regression line, it's always really important to make sense of this. So when we're looking at slope of a line, remember that's the change in y with respect to x. So it's a change in y with respect to x. And really how we interpret this, so our interpretation of this is for every 1 unit increase in x, our y value, and if it's positive slope, it increases by that slope value. And if it's a negative slope, it decreases by that slope value. So that's how we really interpret slope, which is this right here, your interpretation, which is what you're going to need. So your interpretation. So that's how we interpret slope. For every 1 unit increase, whatever we may do in our x, in our explanatory variable, our response variable or our y value increases or decreases by that whatever we have for our slope value. So y-intercept is really meaningful when we have our x value of being 0. So when we can actually take values that are close to 0 for x, that's when we're going to interpret it and try to make sense of it. But if it doesn't make sense when we have an x value of 0, then we don't really interpret it because that wouldn't really make sense in terms of the problem. So if we have a y value, an x value of 0, then our y value is going to be whatever our y-intercept is. And this is kind of our interpretation of our y-intercept. When x is 0, so whatever our x value or explanatory variable is, our y value or response is whatever our y-intercept is. And we kind of touched on this when we have a data set of x and y. We have our linear regression model or least squares regression or LSRL. And we can do that by hand or we can do technology. We did that in the Vitruvian Man activity where we kind of introduced both. But we're going to take a look at just a different example here. So we have some schools have teachers' evaluations done by students. And the students investigated the extent to which the student evaluations are related. So we're looking at correlation here, related to grades that the students got in the class. So we're trying to see if there's any type of relationship between the two or a correlation between the two. Teacher evaluations and the student grades are both given on a scale of 100. The results of Mrs. H's for 10 of her students are given below together with the average of each student's grade, which is X. So here, our explanatory is going to be our grades that the students got. And then our response is going to be whatever the teacher evaluation is. So this is going to be a student grade. And this guy here is going to be our response, which is our teacher evaluation. So student grade, teacher evaluation. So we're going to create an LSRL by hand, and we're going to show all our work, which we did in our Vitruvian Man activity. So remember, we're going to put all of our data into our L1, L2, because we need to use our calculators in order to get our R values, and then our S sub Y and S sub X. Remember, those are our standard deviation of Y, standard deviation of X. So we're going to make sure that we go to our calculators. And we're going to put our stat. We're going to go ahead and go to our list. We're going to clear out our lists because these are not going to be the lists that we want. And I'm going to go ahead and put these in. So go ahead and pause the video and do so because I'm going to do the same thing. Alrighty, so you should have your list completed. So we have our list 1, list 2 over here. When we're looking at our list 1, we should have all of the student grades. And then list 2 is going to be the teacher evaluation done by that student. Remember, they go hand in hand. We have an X and Y ordered pair. That's one singular person. All right. So in order to get our R values, remember we need to go to our our linear regression in number 4. And yes, when you do so, you're going to see your A, you're going to see your B, but we're going to do this by hand and we can check ourselves as we go through. When we look at our R, so remember this is going to be, if you go to your stat, you go to calculate, that's where all of this is. So all of this, make sure you go to stat, go over to calculate, so we press stat, go over to calc, and then we're going to look at our 2 variable statistic, and then we also see this linear regression model here. So you have your 2 variable statistics, which you're going to need, and you're also going to need the linear regression model. If you go down to number 4, this is where we find our R. So you're going to do lin regress. And we have L1, L2. I'm just going to go ahead and enter through. And we have all these values where I have my R, which is 0.90. And we'll do 904. We'll do 3 decimals out. Alrighty. I'm going to go ahead and quit out of that. And we need to now find S sub y and S sub x. So we're going to go back to stat, go back to calculate. We're going to do 2 variables now because we have teacher grade and we also have student grade. So 2 different variables that we're looking at. I'm going to enter. I'm going to enter through. And I'm going to find my S sub x and my S sub y. So S sub y is, or sorry, let's do S sub x first since it's right here. So I have 16 point, let's just round to, we'll do 2 decimals out. So we'll do 3.8. And we'll go down. If I keep scrolling, I can then see S sub y. So S sub y is 24 point, and we'll round to 2.5. So both of those are found in our stat calc, and we're going to do our 2. So both of these are found, if you want to write a note to yourself, underneath 2 variable statistics. So if we're trying to write our equation in the form of y hat equals ax plus b, my slope here is going to be a, and then we'll have our b as well. So which we'll calculate our b here in a little bit. So looking at the next piece, we actually calculate slope. So we take our r and we multiply that by our standard deviation over y divided by the standard deviation over x. So I'm going to take a, my r is 0.904, and I'll multiply that by my s sub y, so 24.25, divided by my s sub x, which is 16.38. And I could type that right into my calculator just as is. So I'm going to put that over here. I'll show you how to type it in. We can clear this out, and I can hit 0.904, and I'm going to multiply that in parentheses, 24.25 divided by 16.38, so I want to do that first, then multiply it, and I get 1.338. So my A value, let's just go ahead and round to the nearest hundredth, so around 2 decimals out. So there's my A value. So that's my slope of my linear regression. And now, like I said before, we can find R, we use that activity. We did the activity before, we're actually calculating by hand, but here we can just find R in our calculator using that least squares regression as well. I'm just going to use that linear regression model, and we'll just go from there. We don't need to calculate it by hand. All right, so finding our y-intercept, our slope, which we just had, which was 1.34. We're going to take our y bar, so remember that is your mean of your y and your mean of your x. So you take your slope times the mean of the x, and you take your mean minus that value. So to find your x bar and also your x or your y bar, remember you have to go back. You got to go back to the 2 and the 2 variable stat. So we're still going to go back to the stat. So you're going to click stat, go over to calc, and then go over to 2 variable statistics. So we're going to go to stat, we're going to go over to calc, scroll down to 2 variable statistics, scroll down to calculate, and we have our x bar, which is 72.4. So I have 72.4. And I want to find my y bar, so I just scroll down, and we have 67.6. All right, so to find my y-intercept, I'm going to take my y bar, which is 67.6. We're going to subtract it from the slope, which is 1.34, times my x bar, which is 72.4. And we'll just type that right into the calculator. So looking at here, we take 67.6 minus 1.34 times 72.4. and it will multiply first before it subtracts. And when I do so, I get negative 29.416. And we can round that to 42. So to create the equation, something that you probably can know about least squares regression lines is that it will always pass through our means of our both. It's just the property that we use to find our y-intercept. But creating our equation, we got y hat is equal to, and we're going to go through and I have my y hat is equal to my slope, because that's my ax. So just remember what we're trying to find, ax plus b, so my a is my slope, which is 1.34. And we said my y-intercept's this guy right here, which is going to be my b. So I have my slope times my x, and then I have minus, and we'll do 29.4, and we'll round to nearest hundredth. 2. Now, the reason why we do least squares regression lines is because we want to make sure that we can predict values. And now this allows us to gather more information and use our equation to predict some values that we want. So, for example, if I want to use our equation to predict what the evaluation that Miss H will get when a student scored an 81 in the class. Okay, so my student scores, remember back to our student scores, 81 is a student. Student grade is an x value. So this is our x value, or our explanatory variable. What we're going to do is use our equation, and we're going to plug 81 in for x to figure out what y is. Our y hat is our predicted teacher evaluation score, which is what we're trying to find, trying to predict what their evaluation score will be. So I got our y hat is equal to, and I'm going to take 1.34, and we're going to plug in 81 minus 29.42. And I plug that into my calculator. So I'm going to take 1.34 times 81, and we're going to subtract 29.42. And I get my 79.12. So we can say, complete sentence, Miss H can expect an evaluation of 79.12 from a student who scored an 81. All right, so next is now interpreting the slope in context of the problem. So remember, my slope is the number in front of the x. It's the x coefficient, which is 1.34. So when I'm looking at this, there's a few different ways that you can kind of word it. So we could say that for every x, so for every 1x, our y is going to increase because it's positive by this amount. So I could say that my x values, remember, are my student grades, right? We just talked about that. My y values are my predicted evaluations. So we could say that when the student's grade increases by 1 point, we can expect Mrs. H's evaluation to increase 1.34 points. So for every 1 of x, our y increases or decreases that certain amount. So we could say that for every 1 point that a student's grade goes up by, Mrs. H evaluations increases by 1.34 points. So we could say that when the student's grade goes up by 1 point, we expect, because it's our expected y, we expect Miss H's evaluation score to increase 1.34 points. Now, the last question that I would like to address is that, do you think that the student grades and evaluations with their teachers are related? So remember, when we look for a relationship, we always look for a correlation. So the correlation coefficient is going to tell us that. And we talked about how our correlation coefficient is 0.904. So if I say that we have our R value is 0.904, well, this indicates, remember, we talk about our strength and how strong or weak it is. And we talk about and also our direction and where it's going. So if it's positive or negative. So looking at our R correlation, and remember, it's always going to be for your form, it's always going to be linear. So we could say that this is a positive because it's a positive R value. It is strong because it's close to 1, and linear relationship between our student grades and our student evaluations. Remember, make sure you're careful about drawing conclusions, saying it's causing, because it's not causing. Correlation, causation are two different things. All we can say is that this indicates a strong, positive, linear relationship between the two variables. So the student grades and teacher evaluation. And we could put score there to make it make sense. And which makes sense, right? Since a student is successful in the class, they'll probably impact how they're going to be relating or how they're going to be rating their teacher evaluations and teacher effectiveness. So taking a look at your least squares regression on your calculator, which we kind of did already, and you kind of know the trick already, but the only thing is that I want to show you is that there are two different ways that we can go about this. If you go to your stat and calc, if you scroll down, you can have your AX plus B, your 4, or you can have your A plus BX. Whichever you decide you want to do, it's going to be giving you the same exact answers regardless. It's just that your A's and B's are going to be switched with your with your slopes and y-intercepts. I like to always use just number 4 just because it's in your y equals mx plus b already, and it kind of is helpful for you to see that correlation or that relationship between the two with that correlation. All right, one other thing that I want to talk about is how we use our least squares regressions to make predictions. Now, before we were making predictions and finding what your values would be if you had an 81 as your score and what the predicted value would be for the teacher evaluation. If we're looking at trying to evaluate new input, that's within the range of the raw data. So, for example, we had our student score of an 81. So 81 was right in here, still within our range of our data, because that score 81 is right in there. We call that interpolating because it's inside. So we're interpolating data. But if it might be within the range. When we're trying to find values of a new input that fall like way outside the range of the data, so if I wanted to find the score of a student that had a 0% or had 130%, that might be way way outside the range of the raw data, and we call that extrapolating. So either interpolating, which is inside, within the range, or we're extrapolating, which is outside the data. And remember, correlation does not imply causation. All it is a relationship, whether it's strong or weak, positive or negative, and it's a linear relationship between the two. The last thing I want to show you is that R squared. So remember when we have the coefficient of the correlation coefficient, and we had our statistics, we had our linear regression, and we had this guy here that is your R squared. That R squared value is called your coefficient of determination. That's what R squared is. Now, this is just the strength of the prediction, so how strong our prediction value is, and how really depends on how close the data points are to the regression line, and that's kind of what your coefficient of determination means. And it's always going to be a scale of 0 to 100%, so you're going to have to use your times by 100 or move the decimal place over 2 times to get what your percentage will be. So when we have an R squared value that is really close to 0, it means it's just less reliable and less accurate at predicting that response variable. If it's close to 100%, it's very reliable, or it's more reliable for predicting your response variable. So in our example, like I just showed you, we have 0.817 or 5, so we'll do 818. So 0.818. So what this means is that 81.8% of the variation in the teacher evaluations can be explained by the linear relationship that it has with the student class average, or the independent variable. I don't like independent. More so the explanatory and response variable. So when we're interpreting this, if you want to put in layman's terms, so for your interpretation, we're going to have our R squared as a percent. So the percent of the data, so percent of the variation of, and we can say our Y variable, because we have teacher evaluations, so of our Y, or response variable, can be explained. And it's important to note that this is by the linear relationship it has with whatever your X variable is, or your explanatory. You have a few questions over least squares regressions and looking at calculating those, putting those values in. You have a worksheet that the teacher will give you.